Hi, my name is Yuhao Zhu. I'm an assistant professor of computer science at University of Rochester. What I like to talk about today is the following. I want to first tell you what is ray tracing, and I want to tell you how does hardware support ray tracing. I'll then talk about neighbor search, and in particular, how is neighbor search related to ray tracing. And finally, I'll talk about how to use hardware ray tracing to accelerate neighbor search. So let's get started. What is ray tracing? Well, so ray tracing is a very much overloaded term. I'll talk about ray tracing in the context of computer graphics, which is about rendering photorealistic images or videos. And one of the most important steps in rendering, in photorealistic rendering, is what's called ray mesh intersection. A mesh, you can think of it as a 3D linear, piecewise linear approximation, which consists of a bunch of polygons, in this case, triangles. And the goal of ray mesh intersection is, given a ray, calculate the XYZ coordinates of the closest hit between the ray and the mesh. And the simplest solution here is exhaustive search. We can iterate through all the triangles, and we can test the intersection for each triangle. And we can then return the closest hit if there's any hit. The complexity of this algorithm is O of the number of rays times the number of triangles, which obviously is very slow because we could have lots of triangles and lots of rays. People have been thinking about how to speed up ray mesh intersection test, and one of the most common ideas is to prune the search space. Essentially, can we search only part of the scene that does intersect the ray? For instance, we can divide the space into different subspaces, and if a ray does not intersect a subspace, then we can safely skip all the triangles within the subspace. And the key question here is, how do we actually partition the space? There are actually a variety of different ways of doing so, and what's very commonly used in computer graphics literature is what's called bounding volume hierarchy. And this is essentially a way of partitioning the object in the space. And I'll use this example to show how the bounding volume hierarchy is constructed and how it's used to accelerate ray triangle intersection test or ray mesh intersection test. So what's on the right is a scene with, let's say, 4 triangles. And for each object or each triangle in the scene, we figure out its bounding box. So let's say triangle 1 here has the bounding box C. And let's say we also decide to group triangle 2 and 3 to bounding box D. So this D would have 2 children, triangle 2 and 3. And C and D is bounded by this box B. So we add that node B to the tree on the left, which has 2 children, C and D. And let's say triangle 4 is bounded by box E. And then eventually box B and E are bounded by A, which is the root node of the tree. So the terminology here is that C, D, E are the leaf nodes of the BVH tree. Each leaf node is associated with one or a set of primitives, which in this case are triangles. And A is the root node here. And A, B, C, D, E here are what's called the axis-aligned bounding boxes, or AABBs, because these are bounding boxes whose faces are aligned with the axis. You could have other irregular bounding volumes that has their own trade-offs, which we're not going to talk about here. So let's see how you can use BVH to accelerate ray triangle intersection test. With a ray, what we're going to do is to start from the root of the tree and to test whether the ray intersects with the tree. If it does not intersect with the root node, then it's guaranteed to not have intersection with any triangles. So in this case, it does intersect with A. What we're going to do is to push its children B and E onto the stack, and then test the ray against B. In this case, it does intersect with B. We're going to push C and D, the children of B, onto the stack and test against C. In this case, it does not intersect C, so we can safely skip triangle 1 under C. And then we perform a further test against AABBD, which does intersect with the ray, and then we iteratively test against the triangles within D, which in this case are triangles 2 and 3, and we can realize that the closest hit so far is going to be with triangle 2. and then we pop E out of the stack, the ray does intersect with E, but the intersection point is farther away than the intersection with triangle 2, and so we can skip everything under E. Essentially, we can stop and finish the intersection, and we can know that the closest hit is with triangle 2. So as you can see, using BVH to perform ray mesh intersection test in turn requires a sequence of ray AABB intersection test. And this test is quite intuitive in the sense that we just have to calculate the hit point between the ray and the AABB, and if the hit point is within the ray segment between Tmin and Tmax, then that is an intersection. However, here is a subtle but very important case that we're going to make use of later, and that is if a ray segment is completely within an AABB, it does not intersect with the AABB, we still have to treat it as intersecting, because it is possible that there is a smaller AABB that does intersect with the ray segment. And so we have to treat the ray to be intersecting with a larger AABB so that the smaller AABB is given the opportunity to be intersecting. And this is a point that we're going to make use of and come back later. So that is the ray tracing algorithm, and let's now talk about how modern GPUs support ray tracing. The first thing we realize is that ray tracing is embarrassingly parallel because every single ray is completely independent of each other. So a GPU is a natural fit for performing ray mesh intersection test. What we would do is to first build the BVH, and we assign each ray to a thread. What each thread does would be to first traverse the BVH, which requires managing the local stack, and perform a sequence of ray AABB intersection test. Once it gets to a leaf node of the BVH, it would do ray primitive intersection test. For instance, in the case of triangular mesh, it would perform ray triangle intersection test, and it would execute, for instance, a shading algorithm to calculate the color. Now, what's important here is that some of these steps are more or less fixed functions, such as building the BVH or traversing the BVH or performing ray AABB intersection test, whereas other steps need to be programmable, such as performing ray primitive intersection test, because that depends on what the primitive really is, whether it's a triangle or a sphere or so on. So realizing this, NVIDIA proposed the optics programming model, which is a ray tracing pipeline where some of the pipeline stages are programmable and others are fixed functions. And in the Turing architecture from 2008, NVIDIA uses RT cores which to accelerate the fixed function stage, and the programmable stages are executed on the conventional CUDA cores. And this is how an SM looks like in Turing GPUs, where you can see that within SM there are conventional CUDA cores, and there is the RT core which is used to execute the fixed function stage, and in particular the BVH tree traversal. Now let's talk about neighbor search, and in particular how does it relate to ray tracing. There are different forms of neighbor search. The first kind of neighbor search I'll talk about is what's called range search, where given a query, we want to find all the neighbors that are within a particular range or radius. Now, in reality, we would also limit the total number of neighbors because of practical memory constraints, and also because downstream algorithms typically expect a fixed number of neighbors. And for that reason, the search interface typically looks like this, where we take a query and we want to return k points that are within the range of that particular query. Another kind of neighbor search is k-nearest neighbor search. For instance, in this case, we want to find the two nearest neighbors. Usually, we also in KN search we also limit the range of the neighbors, because neighbors that are too far away, even though it is the k nearest neighbors, but if they are too far away, they're of no significant importance. For instance, the force that a remote particle exerts on the current particle would actually be very small. So the query interface for KN search would look very similar, except it would return the k nearest points that are within the range of a query. And in particular, we're going to focus on low-dimensional search. When I say low-dimensional, I mean between smaller than 3D. And low-dimensional searches are very prevalent in computational science and engineering fields, such as computational fluid dynamics, graphics, and computer vision. They all manipulate physical data, such as particles and surface samples, that are inherently residing in 2D or 3D spaces. High-dimensional searches require very different algorithms because of the curse of dimensionality, and they are out of the scope of our current work. And the idea of neighbor search that this paper takes is to turn the problem around. And let's use range search as an example here. Range search requires us to find all points within R from Q. Instead of doing that, what we're going to do is to find whether Q is within R from other points. In other words, we're going to generate spheres of radius R and test whether a particular query is within the sphere of a search point. And this is what we call the point in sphere test. Now, how do we do that? We're going to do that in 2 steps. First of all, we're going to ask, is Q in the AABB that circumscribes the sphere? And if Q is not in the AABB, then the Q is guaranteed to be not within the sphere. And this allows us to prune remote points. If Q is within the circumscribing AABB, we can then further test whether Q is in the sphere, at which point we calculate the distance between Q and the search point and compare against the radius. Okay, so if you look at the first point, the first step, which is essentially a point in AABB test. How do we do that? Well, recall that any ray that's within AABB must be treated as intersecting. So our idea here is to generate a very short ray from Q and ask the ray tracing course to perform the ray AABB test. Because the ray is very, very small, that ray is guaranteed to be intersecting with AABB, and then we know that Q is residing in the AABB. And this is also the reason why we have to use a very short, very small ray. Because if we use a long ray, then a query that's outside of the AABB could also be intersecting with the AABB, but the query itself is actually outside of the AABB. So this leads to false positives that we don't want. Now, with all these, now let's talk about how we can use hardware ray tracing to accelerate neighbor search. The idea here is that given a bunch of search points in a query, we first create an AABB of width 2R, where R is the search radius, for every search point. And then we construct a BVH from the AABBs, and this is the step that we have no control. This is hidden behind the optics APIs and most likely down on the hardware. And let's say that that's how the BVH looks like for the example I had. Note that in this case, the primitives are no longer triangles. They are spheres here. And then we generate a ray for each query, and we then use that ray to traverse the BVH, essentially skipping those non-circumscribing AABBs. And again, this is done in the hardware and accelerated by the RT course. When we get to the leaf node, we can then calculate the distance between the query and the point, essentially allowing us to gather the neighbors. And we can keep traversing the tree until we finish finding all the neighbors. If you were to just implement this, it would actually lead to very slow performance for 2 main reasons. The first reason is control flow divergence. And the problem is that optics will inherently group every 32 adjacent rays into a warp. And if these adjacent rays are spatially apart, they are going to be exercising different nodes of the tree, creating control flow divergence. For instance, query X is going to be exercising these nodes, and query Y is going to be exercising these nodes. And as a result, we might have lots of control flow divergence, which is bad for GPU performance. So our idea here is very natural. It's to group or to order queries spatially. The intuition is that we should group spatially close queries together so that their arrays could follow similar traversal paths to reduce the control flow divergence. And in the graphics parlance, this is called improving the array coherence. How do we do that? Well, a very simple heuristic is that queries enclosed by the same AABBs are spatially close. Note that a query might be enclosed by many AABBs, but any AABB will do. How do we find one? Well, the idea is we can cast an array and immediately terminate the array once it hits the first leaf node. And there's an optics API for that. And essentially, we effectively return the ID of the first enclosing leaf node, leaf AABB, and use the ID as a key. We can then sort by key. That allows us to naturally sort queries spatially. And this is sort of the pseudocode for that. We would first build the BVH and trace all the arrays once to find the first hit AABBs and use the first hit AABBs as the key to sort the queries, and then launch the ray tracing the second time. The second problem has to do with large AABB sizes. Strictly speaking, the AABB width must be 2R. Now, what if we can find k neighbors in a smaller range? Well, we could, in theory, use a smaller AABB. Why do we need to use a smaller AABB, or what's the benefit of using that? Well, using smaller AABBs would drastically reduce the search time. So on the figure here, in the figure here on the left axis, I'm showing you the AABB width. On the y-axis, I'm showing you the search time. And as you can see, the search time is strongly correlated with the AABB size. Why? Because smaller AABBs means that a query is enclosed by fewer AABBs, which leads to fewer traversals and fewer shader cores. And this is particularly important for KNN search, where every shader would manipulate a priority queue. So that leads to our idea of query partitioning. The idea is that for each query, let's find an AABB size that's just large enough. In this example, if we want to find the 4 nearest neighbors, then the smallest AABB would be one that's with D rather than 2R, which, as you can see, the smaller AABB the new AABB is much smaller. And illustratively, what we're going to do is to partition these queries according to their corresponding AABB size, and we're going to group them together. And for each group or partition, we will have to create a dedicated BVH, and using that BVH to do the search. So this is essentially trading BVH construction overhead for faster search. The one problem that we haven't talked about is how do we determine the AABB size for a query? And this would actually vary depending on the search type. So I'm going to talk about how to determine AABB size for a range search. And the goal here is to find the smallest AABB that actually contains k neighbors. And the idea is to create a uniform grid over the scene, and we start from the central cell and iteratively grow and collect neighbors until we get the k neighbors. So we start from the cell that contains the query and iteratively grow along all 4 directions in the case of 2D search, or 6 directions in the case of 3D search, and we stop until k neighbors are found, or when the sphere boundary is reached. And so we call the final collection of cells the mega cell, and the mega cell in this case has a width D. And D is naturally the AABB size. Due to the time limit, I won't talk about how we determine the AABB size for KNN search, which turns out to be slightly more subtle, which we can find in the paper. In the paper, you can also find how we can optimally bundle the partitions, because as I said, query partitioning is essentially trading or increasing the BVH construction cost to reduce the search cost. So there's a sweet spot, which we talk about how to identify in the paper, and you can also find implementation details. So I want to quickly talk about some high-level results. We implement this using optics 7.1 and CUDA 11, and we perform experiments on RTX 2080. And there are 4 different baselines that we compare against. CUN search is a grid-based neighbor search implemented in CUDA. It's used in the very popular split splash fluid simulation. FRNN is a grid search implemented in CUDA. This is a drop-in replacement for neighbor search in PyTorch. PCR Octree is an Octree-based CUDA neighbor search implemented in CUDA. It uses Octree rather than BVH to prune the space. And faster RNN is a KNN search implementation using RT cores without our optimizations, including query partitioning and query ordering. And we use 3 datasets, Kitty stand for 3D scanning repository, as well as n-body simulation to cover different application domains. So in this figure, on the x-axis, I'm showing you different applications in the benchmark, and the y-axis shows the speed up of our implementation of our search algorithm, RTNN, over different baselines. And as you can see, the range search speed up ranged from 2.2x to 44x, and the KN search speed up ranged from 3.5x to 65x. And there are 2 high-level trends. One is that the speed up is higher naturally on larger inputs. So for instance, if you look at Kitty going from 1 million points to 25 million points, the speed up increases accordingly. And the second trend is that the speed up is generally higher on KN search over range search. And the reason is because KN search is more time consuming to begin with because it must manipulate a priority queue. So these slides compare against different variants of our search algorithm by teasing apart the effects of different optimizations, going from the baseline without any optimization, so that's the slowest, that's the leftmost bar, and adding scheduling, which is query reordering, it significantly improves the search time. And by adding query partitioning and query bundling, we further improve the search time. Note that the y-axis is in log scale, and so even though the improvement might seem significant, the gain is actually non-trivial. So I have demonstrated a way of formulating neighbor search as a ray tracing problem and using ray tracing hardware in emergent GPUs to accelerate neighbor search. And there are actually quite a few examples of using RT cores and ray tracing hardware for non-graphics workloads, things like motion planning in robotics. And the key is to really formulate a problem as a BVH search, because that's what RT cores are built to do. But this also limits the applicability of RT cores because BVH search is a very specific kind of search. So if we think of today's GPUs as really GPUs that execute or that accelerate general purpose regular applications, it would certainly be interesting to think about how to generalize RT cores so that they become sort of general purpose irregular accelerators. With this, I'd like to thank you all for paying the attention, and feel free to leave any questions and comments and send us emails. Thank you.